So good afternoon, everyone. I'm Cozlin. I'm a PhD student from La Rochelle University in France. And today I'm going to talk about the impact of hydrogen microstructure interactions on fracture behavior of an additively manufactured Inconel 718 alloy. So first, a little bit of context. As you may know, hydrogen is very detrimental to the mechanical properties of alloys and can lead to brittle intergranular failure. The microstructure of the material is very important regarding hydrogen embodiment. And on the other hand, new manufacturing processes, such as additive manufacturing, can provide new original microstructures. So in this context, the study focuses on the interaction of on hydrogen microstructure interactions of an additively manufactured alloy. And more precisely, we're going to focus on three types of defects. So grain boundaries, precipitates, and dislocation. So the material studied is Inconel 718 alloy produced by additive manufacturing and more precisely by electron beam melting method. This process is shortly described on this slide. And the as-printed parts are subjected to different post-treatments. So first, a hot isostatic pressing treatment, followed by a recrystallization and annealing heat treatment. So we have three different conditions: as-printed, heaped, and recrystallized. So if we take a look at the characterization of as-printed samples, we observe a fine columnar dendritic structure with some regions of equiaxed dendrites. If we zoom in, we can see that we have precipitates aligned along the building direction in shape of needle, which are identified as delta precipitates. Also, our samples we observe some porosity in the sample, which was characterized by XCT. And you can see on this graph, two populations of porosity. The first one with a high compactness and sphericity, which correspond to gas porosity. And the second one with a low sphericity and a low compactness, corresponding to lack of fusion. The average porosity level was 0.22%. Then BSD analysis highlights a strong cube texture, typical of additive manufacturing alloys. And when we look at grain boundary statistics, we observe that we have a high fraction of high-angle grain boundaries, which are composed mainly of random grain boundaries. Then TEM images highlights delta precipitates and also the hardening gamma prime, gamma double prime precipitates. Also, we observed a higher dislocation along the subgrain boundaries than in the matrix. Okay. After heap treatment, now we have a very low porosity fraction, and the precipitates such as delta, gamma prime, and gamma double prime are dissolved into the matrix. So the material is more homogeneous, and this is confirmed by the constant hardness along the build. If we take a look at the grain boundaries, we still have the same fraction, but we do observe a slight increase in spatial grain boundaries fraction. So we don't see very well, but for dislocation structure and precipitates, we again have a higher dislocation density around along the subgrain boundaries. And we have identified small hardening gamma prime and gamma double prime precipitates. For the last condition, now we have a completely equiaxed grain structure with random orientations. And now we have a very large increase in spatial grain boundaries. And almost all of them are coherent twin boundaries. The TEM images show that we have a very low dislocation density and a microstructure free of precipitates, except for some carbides or oxides. Now for the mechanical testing, we did use a tensile micro machine at a strain weight of 10 to the -4 and at room temperature. We did test two directions, so parallel and perpendicular to the building direction. And the true stress and true strain data were derived from these equations. So first, without hydrogen, you can see here on this slide, the true stress, true strain for each condition and for the two directions. So first, we see that we have an increase of elongation at failure and a decrease of yield strength with heat treatments. So the material became more ductile. Then we also observe anisotropic behavior, especially for as-printed and hipped conditions, which is attributed to the columnar grain structure. Also, we see that the specimen tested perpendicular to the building direction exhibit better mechanical properties. If we take a look at the fracture surfaces for as-printed condition, tested parallel to the building direction. So first, we see that we have a large lack of fusion pore and some regions with local group of voids, which may be due to shrinkage or gas porosity. For the sample tested normal to the building direction, we don't see any lack of fusion, but we can see the dendrite microstructure. For the hipped and recrystallized specimen, we have a dimpled and ductile fracture, and we can observe finely distributed oxide particles on the healed regions of lack of fusion. Now, this slide, we can see the impact of hydrogen. So here you can see for specimen tested perpendicular to the building direction, we can see that hydrogen leads to a decrease of elongation at failure and also a decrease of UTS for each condition. But we do observe an antagonist effect. For example, for as-printed condition, we observe a hardening effect while we observe a softening effect for hipped and recrystallized conditions. The as-printed sample seems to be more sensitive to hydrogen due to the hydrogen abutment index value. But we can wonder if this is due to hydrogen or maybe to porosity. Indeed, when we look at the fracture surface, again, we can see a lack of fusion with unmelted powder inside. And we can see on the edges of the sample, brittle intergranular failure with thickness depending on the diffusion coefficient. So if we measure the penetration depth of hydrogen, we can estimate the diffusion coefficient, which was about 9 to the -16 square meter per second. Also, we observe some grains with slip bands and endovoid coalescence and the equation between matrix and precipitates. So for hipped and recrystallized, we didn't see any porosity, but we saw a brittle area and a ductile fracture on the bulk of the specimen. So we were able to see grain equation and slip bands too. Same observation for the recrystallized specimen. So if we measure the thickness of the hydrogen affected area, we can estimate the diffusion coefficient of around 4 to the -15 square meter per second for both conditions. So to conclude on this study, we saw that on the hydrogen diffusion behavior, for the as-printed condition, we have a lower hydrogen penetration depth, even though this condition has the highest fraction of random grain boundaries. So we can wonder if there is any influence of delta phase or porosity on the hydrogen behavior. On the mechanical properties, on the mechanical properties, we saw that we had different behaviors. First, as-printed condition experienced experienced hardening effect, while heaped and recrystallized sample experienced softening effect. And hydrogen embuttement index depends on both porosity, as we saw for as-pointed condition, and the fraction of special grain boundaries, for example. So we saw that we had a thin hydrogen-affected area on the edges of the sample. So we can say that the material behaves like a composite with a thin, with a soft and ductile bulk enveloped by a brittle shell. So thank you for your attention, and if you have any questions.